G'day guys, welcome back. In this particular video, I'm going to be talking about a fairly simple springs problem. What is the total length of a spring, L, that has a 3 kilogram bucket of water dangling from it? So what's happening here is we have a spring just here, and dangling from it is a 3 kilogram bucket of water, and we're asked to find the total length of this stretched spring, capital L. Now, in order to solve this problem, we'll need to know some properties of this spring. Fortunately, they're given to us. We know that the spring stiffness is K, which is 40 newtons per meter, and we also know that the unstretched length of our spring, L0, is 30 centimeters. Now, in case you're a little bit unsure about what the unstretched length is, let me just draw our spring again without the bucket attached to it. So this is our spring without our bucket attached to it, right? Notice it's going to be shorter here because there's not a weight pushing this thing and stretching it out. Right, so in fact, this right here will be our distance L0, right? This is your distance L0. It's the length of your unstretched spring. Okay, now that we've got the basics covered, let me now start this problem the same way pretty much every dynamics problem should ever be started, with a free body diagram. So let me draw our bucket just here. This is our bucket, and it's got water in it. And let me draw the forces on this thing. Well, there'll be a force due to gravity on this bucket, right? This thing has mass, so there will be a force due to it from gravity, which will be mg, right? Where m is 3 kilograms and g is 9.8 meters per second squared. There's also another force on this bucket. There will be a force on this bucket upwards, which will be kx, right? This is from Hooke's law. Now, K is your spring stiffness, as discussed before, and X is the amount your spring has been stretched from its unstretched length, right? So what I'm saying is X is going to be this distance just here. Remember, in Hooke's law, this is always the amount it's stretched from its unstretched length. Now we're ready to start using Newton's laws. We know that the sum of forces acting on any particle is going to be equal to ma, right? Well, because this bucket of water is dangling, that means that this thing is not moving, which means our acceleration is actually 0, right? So to reevaluate this, the sum of forces on a particle is equal to the mass of that particle times the acceleration of that particle. In this case, our bucket is our particle. And our acceleration is 0 because the bucket is just dangling from the spring. The bucket isn't moving anywhere, so the acceleration is 0. That's all I've said. Now we're ready to complete this formula. It's going to be the sum of forces must be equal to 0, right? Because this is 0 just here. What's the sum of forces on this thing? Well, we need to define an axis. I'm going to define x being here and y being here, our standard Cartesian axis. So that means by notation, our spring force is upwards and is positive. So this is going to be kx, and it's positive because it's upwards by our convention. Now our force due to gravity is downwards, which is negative by our convention, so I'm going to subtract it from mg, right? And that's going to be equal to 0, like I've mentioned before. Okay? And of course, now we can solve for x, right? And I know x isn't what we're going to look for, but trust me, it'll come in handy. We're going to solve for x, and we know x is going to be equal to mg divided by k, and when you plug that into your calculator, you're going to get, let's see, it'll be 3 times by 9.81 divided by k, which is 40. Notice all of these units are in Newton meters, so I can just plug it straight in, and that'll give 0.73575 meters. So let me get this straight. X is the amount your spring has been stretched, and we've just proven by applying Newton's laws that X is equal to this beast just here, right? So this is going to be X just here, okay? But we're asked to find L. Fortunately, we know that L0 plus X is equal to this giant capital L, right? And that's basically saying your unstretched length plus the amount the thing's been stretched equals your total length of your spring. So we know that L0 plus X is equal to capital L. And if you plug in the values, remember, this is 30 centimeters. In SI units, it's going to be 0.3 meters plus x, which is 0.73575, and that's going to be equal to 1.04 approximately, right? So this is going to be equal to L. So we've proven that your total length of your spring is about, and I've rounded it to this amount of decimal places, it's going to be 1.04 meters. This is the length of your spring when there's a 3 kilogram bucket of water dangling from it. Okay, guys, that's that video. Cheers.